Yeah, in the yesterday's lecture, we discussed about the semiconductor introduction as well as energy band theory. That is, say suppose in any atom, okay, let us consider the atomic number. It is 26. Okay, I can write the electronic configuration as 1s2, 2s2, 2p6, 3s2, 3p6. That is 20. Okay, 4, 10, 18, 20, 20. Here it is 6 electrons are there. Okay, okay, fine. Now here it is that point of concentration, it is the two electrons in the 4s subshell will have the similar energy. Okay, suppose let us consider this is the energy level in the ground state. Suppose let us consider E1. E1 is the energy corresponding to the 4s electrons, two electrons. So we'll have the each electron will have energy level, almost similar energy. Okay, almost similar energy. Okay, the two electrons will have the similar energy. That means here it will forms a band. Okay, this one. And these six electrons will forms a band. Okay, now you can see here it is these six electrons are from the third orbit. Okay, so I will consider E2. It is the energy due to 3D. Okay, subshell. Okay, all the six electrons, it is having a somewhat less energy. We can say that E1 will be greater than E2. Antenna, E1 will be greater than E2. That means here we are having six electrons. 1, 2, 3, 4, 5, 6. Okay, all the six electrons will have the same energy level. Okay, that is approximately, this is for one electron, like that six electrons. So these E1 and E2 will forms a band, and this band is formed due to valence electrons or outermost electrons. Okay, valence electrons are outermost electrons. Hence, these bands can be called as valence band. Can be called as valence band. Okay, and now whenever we supply the energy, that is the light energy, in the form of NH nu, each electron will absorb the energy and will be excited to the highest energy state. That is, these 4s electron will be excited to the 4p, will be excited to the 4p subshell. Okay, that is, I'll write as argon 4s1, 3d, 4p1. Can I write in the first excited state? In the second excited state, we can write it as argon 4s0, 3d6, 4p2, right? Antenna. Okay, now it is for 3D. This is the first excited state of the 4s electrons. Okay, here we are having the two states like this. First excited state and second excited state. Suppose this is first excited state and this is second. Similarly, all the six electrons are from the same subshell will be excited to the excited state. Okay, we'll have first excited state and similarly we are having the second excited state. That is, in this excited state, electrons will be in the, okay, electrons will be in the conduction. Okay, electrons will be in the state of conduction. So we can call it as an conduction band. Okay, we can call it an conduction band. The gap between the okay the gap between the lowest energy level of conduction band and highest energy level of the valence band, that means this one, can be called as energy gap. Energy gap. Okay, once again I will repeat. Energy gap, it is the difference in the energy level of lowest energy level, lowest energy level, or we can say state of conduction band and highest energy level, highest energy level of valence band, can be called as energy gap. Okay, each some textbooks, the what they will write it is energy gap will indicate with eg, or we can write as delta e, we can write as delta e. Okay, now here we need to examine the energy gap for conductors and insulators, and as well as semiconductors, as well as semiconductors. What will be the energy gap for this one? Energy of conduction band minus energy of the valence band. Okay, okay, fine. Now here it is that, here it is, whenever we excite it, what will happens at, there will be some level at which, see this, these two are from the 3D electrons. That means all the 6 electrons, okay, in conduction, in conduction, suppose. Okay, whenever the, as the valence electron increases, the number of electrons in the conduction band increases, such that there will be more number of electrons will be in conduction. Here I'm having 6 electrons are there. Suppose if I'm having here, okay, more than 10 electrons, more than 10 electrons, that is in the F subshell, especially in lanthanides and actinides, will have maximum occupancy in F subshell, it is 14. Okay, if I'm having more than 10 electrons are there, whenever the 10 electrons are combining, then what will happens? One electron will combines or coalesces or superimposes with another electron, such that the energy states will be combines, will be combines. Okay, all of you have board textbook, either CBSE or TS board or Andhra board, any board
No, sir.
textbook. Tomorrow I'll show you how these states will combine. Tomorrow I'll show you how these states will combine. That is theoretically only. Numerically only, they are asking that it is energy gap. This one. Okay. Okay. For conductors, what will happen it is that, suppose this is the conduction band, this is the valence band. Suppose let us consider this one like this. Okay, so here it is the, this is the lowest level of conduction band, right? Okay, and this is the highest level of the valence band, this is the highest level of the valence band. So the energy difference between the lowest level of conduction band and highest level of valence band can be called as energy gap. Now for conductors, we can take, conductors means I can say the example as all metals. You can take any metal. Okay. Can you say the example of metal? Any metal? Metals. lithium, sodium, potassium, okay,
Magnesium.
magnesium, okay. That is the substance which is having more electropositivity nature, more electropositivity nature. We can consider. For these substances, what will happens? We know that for conductors, if we give small amount of potential, electrons will flow inside the conductor, right? Similarly, if we give small amount of energy, the electrons or valence electrons in the metals will will be excited to the first excited state, and thereafter second excited state, and thereafter third excited state, and so on. So here the energy gap between the conduction band and valence band, it is very much low, very much low. Okay, that we'll see now. Okay. Suppose let us consider this is the series of valence band. Okay, like this we are having the series. Okay, like this is the conduction band. This is the conduction band. So this is the gap. You can see here the energy gap. The energy gap for conductors, it is approximately 0 electron volt. Very very less. Okay, Eg will be very less for conductors. Eg will be very less for conductors. Okay, number one. Next, number two, it is I will go to the insulators. Thereafter, I will come to finally I will come to semiconductors. For insulators, okay, that is we can say that example for insulator, we can say that it has plastic or all non-metals. Chapacha, can I say? Hello? Hello?
Yes, sir.
Anna? All non-metals, we can consider it as an this one. Okay, fine. That means in the non-metals, what will happens? Here also we'll have the valence band. That is energy levels will have like this. This we can consider as valence band. Okay, and here we are having the energy levels. Okay, that means whenever we give large amount of energy, that is in the order of greater than 1000 electron volt or 10,000 electron volt, okay, then the electrons in the valence band will be excited to the conduction band or will be excited to next higher states. So the gap between lowest level of conduction band and highest level of valence band will be greater than 7 electron volt, greater than 7 electron volt. Okay, fine. Okay, so Eg energy band gap for insulators, it is high. Insulators is 7 electron volt and it is the high value. Okay. Okay. According to the definition of semiconductors, okay, we can say that it is semiconductor is a material whose conductivity lies between the conductivity of conductors and conductivity of insulators. Avuna? Semiconductor is having a conductivity which lies between conductivity of conductors and insulators. Like that, similarly, here we are having a valence band. Okay, suppose let us consider this one. We are having the valence band, and here we are having the conduction band. Okay, okay, fine. This is the conduction band. Then what happens it is, okay, this Eg will lies in between from 0 electron volt to approximately 3.5 electron volt, right? Antena. So here we can say that Eg is greater than 0 and Eg is less than 3.5. So this one I can write as 0 less than Ag less than 3.5 electron volt. Can I write? Can I write? This is for semiconductors. Okay. Okay, fine. Now these semiconductors, here we are having the, okay, here we are having the different types. Okay. Initially we are having the number one, elemental semiconductor. Elemental semiconductors. That is a single substance which is in the atomic state, okay, will behave as a semiconductor. That is like silicon, germanium, gallium, indium, okay, and then arsenic, etc. Okay. Next, second one it is compound semiconductors. Compound semiconductors. Compound means that it is a, the substance is having two or more substances. Okay. Say for example, gallium arsenide, indium phosphorus. Okay, like this, etc. Like this type of compounds can be called as compound semiconductors. Compound semiconductor. Apart from these, okay, we are having out of 110 elements, approximately one or two elements will act as a semiconductor. Will also act on the okay, one or two elements will behave as a semiconductor. How we can do this much means semiconductors is broadly divided into two types. Semiconductor is broadly divided into two types. That is, number one, it is intrinsic semiconductor, and another one it is extrinsic semiconductor. Extrinsic semiconductor. Intrinsic semiconductor, it is the pure form of semiconductor which are available in the earth crust. Okay, earth లో ఓకే జనరల్గా లేకపోతే సహజంగా దొరికే గుణాన్ని ఏమంటామంటే ఇంట్రిన్సిక్ సెమీ కండక్టర్ అంటాం. విల్ కాల్స్ an intrinsic semiconductor. Okay, now extrinsic semiconductor, it is the impure form. Impure form. Impure form means, suppose let us consider phosphorus is there. Okay, phosphorus is there. For the phosphorus, what will happens? We are having the configuration as, okay, 3s2 3p3. 5 electrons are there. Hello? 5 electrons are there. By adding some material, we are making this phosphorus into a semiconductor. Okay? Whatever we are adding, we'll call that as an dopant. Dopant means added material. And the process, can be called as doping. Okay? Doping అన్న పదం ఎప్పుడైనా విన్నారా? హలో? Hello?
No, sir.
Doping. Okay? You can see, okay, especially in the ఒలింపిక్ గేమ్స్ అవుతున్నప్పుడు
Doping
ఏమవుతుంది?
test,
డోపింగ్ టెస్ట్ అంటారు. ఇప్పుడు వచ్చారు. ఇప్పుడు ఆ
drugs testing.
డోపింగ్ టెస్ట్ అంటే ఏంటి అసలు చెప్పండి?
డ్రగ్స్ తీసుకోవాలి తెలుసు
ఏదైనా కెమికల్స్ తీసుకున్నా లేకపోతే ఏదైనా తీసుకున్నాడా అని టెస్ట్
తెలుసు.
చేస్తారు. ఓకే? అట్లాగే ఇక్కడ డోపింగ్ అనేది కూడా ఏంటంటే, నేను వేరే ఏదైనా ఒక మెటీరియల్ యాడ్ చేస్తే ఆ ప్రాసెస్ని మనం డోపింగ్ అంటున్నాం. ఏ మెటీరియల్ తోటి యాడ్ చేస్తున్నామో దాన్ని డోపెంట్ అంటున్నాం. ఓకే? ఓకే. హియర్ ఐ కెన్ హ్యావ్ ద టూ టైప్స్ ఆఫ్ డోపెంట్స్. One is trivalent and another one is pentavalent. Okay? Trivalent means 3 electrons. Okay? Pentavalent means 5 electrons. Here in the phosphorus, I am having in the valence electron 5 electrons are there. So phosphorus requires another 3 electrons to attain the inert gas configuration. Right? Inert gas configuration, so that it can behave as a semiconductor. Okay? Suppose if any substance, let us consider 2s2, 2p6, 3s2, 2 electrons are there now. 5 రావాలంటే 3p1, right? Fine. Now see here, we are having 10, 13. Aluminum is there. Atomic number is 13. In the valence electron, I am having 3 electrons. It requires another 5 electrons to attain the inert gas configuration. So, by adding 5 electrons, okay, to the aluminum, then aluminum will become as an extrinsic semiconductor. So here we are having the techniques or processes, okay, to bring a substance or any chemical, okay, out of these 110 elements we can bring any chemical or any element into the semiconductor. Okay, that type of semiconductor can be called as extrinsic semiconductor. That type of semiconductor can be called as extrinsic semiconductor. Okay? Okay, fine. Firstly, before going to see the trivalent and pentavalent, okay, firstly see the bonding in semiconductors. Bonding in the semiconductor. Say for example, okay, what we know is that it is example for semiconductor, it is silicon, or you can take germanium, anything. I will consider silicon. Silicon is having atomic number as 14. Okay, it is having an electronic configuration as 1s2, 2s2, 2p6, 3s2, 3p4. Okay, అంతేనా? 10, sorry, 2, 3p2, 4 plus 6, 10 plus 4. Okay, 3p2. So silicon is having 4 electrons in the valency shell. Okay, if I add another silicon, if I add another silicon, that means here we can write it as, or here we can draw it as silicon. The 4 electrons in the first silicon atom will be mutually shared with the 4 electrons in the second silicon atom. So due to the sharing of electrons, there will be a covalent bond will be formed between the silicon, right? Antenna. So we can say that covalent bond formation, covalent bond formation will exist, will exist in semiconductor. Okay, will exist in semiconductors. Okay, suppose let us consider metals. In case of metals, what type of bond will exist? In case of metals, what type of bond will exist?
Ionic bond.
Ionic bond. Okay. In case of insulators, will there be any bond formation? Will there be any bond formation? Hello? Will there be any bond formation? ఉంటుందా
No, sir.
right? Okay, I know here covalent bond in semiconductor, ionic bond in metals. Okay, fine. Now here the point it is coordinate covalent bond is there. This coordinate covalent bond exists in what type of substances? Covalent bond will exist in both as well as in metals, okay, as well as in alloys, as well as in alloys. 1 minute. Coordinate covalent bond will exist in metals and in alloys. Okay, okay. This one we don't require. Sometime in the NEET they asked what type of bonding will exist in metals and semiconductors. That's all. Okay. Suppose see here. Let us consider the. I am having a silicon atom. Okay. If I extend it. Okay. Like this, we are having the structure. Avana? Hello. Hello. Hello.
Yes, sir.
Like this, here we are having the structures. You can see everywhere 4 electrons we are having. like this. Here we are having that each atom is having the 4 electrons are there. Okay. Now you can see here these 2 electrons will forms a bond with these 2 electrons, and similarly here it is. These 2 electrons will forms a bond, and here also. Okay. Okay, such that the above 2 electrons will forms a bond. So this atom is having 8 electrons, and here also 8 in the middle row and the bottom. Now in the top row you can see 2 electrons and 2 electrons here shared. Here 2 electrons will be shared with the beside atom. Will be shared with the beside atom. Like that, bonding will be formed in the semiconductor. Okay, like that, bonding will be formed in the second row and in the third row. Okay, we are having the each atom is having 8 electrons. Okay, here bonding is between these two. So here I got the 4 electrons out of it. I got. Here these 2 electrons will get sharing with the beside atom. So due to that, will have this silicon atom also will have the 4 electrons. Okay. Hello. Okay now. Okay, fine. Now here we are saying that electrons. Suppose 8 electrons or anything, or 6 electrons. In the energy shell, okay, this is the valence band, and here it is a conduction band. Suppose let us consider I am having the 4 electrons are there. If one electron is excited upon supplying of energy, one electron is supplied, then what will happens? Then what will happens? Okay. That is, in an atom, I can see the major constituents of the particles are electrons, protons, and neutrons, or subatomic particles as electrons, protons, and neutrons. Antena? Hello? Antena? Electrons, protons, and neutrons. Similarly, we are having that it is what are the major particles in an semiconductor. Whenever an electron is excited to highest energy shell or highest energy state, then what will happens around this we are having an electronic charge into the up to some distance will have the effect of charge of electron. అవునా ఉంటుందా?
Yes, sir.
Okay. Now, according to the charge conservation, okay, according to the charge conservation, okay, we need to conserve the charge first. Why we need to conserve the charge? Means whenever we are having unequal number of protons and unequal number of electrons. Say for example, if I consider sodium atom, 11 electrons and 11 protons. Sodium ion Na plus, 1 electron is removed. That means 10 electrons and 11 protons. Avuna? Hello? Antena? Around this 1
Yes, sir.
electron, we are having 1 proton is there. So due to that, here the total charge is stabilized or conserved. Suppose if I am having Na2 plus or Na3 plus, 9 electrons, 11 protons, unequal number. So this type of substance will be unstable, will be dissolved very quickly, very quickly. This type of substance will be dissolved very quickly. Okay, now? Okay, fine. Now, suppose here it is, whenever an electron is excited to its highest energy states, we'll have an, up to some distance, we are having the effect of charge of electron. This one, we can call it as electron cloud.
The 10 things in this picture. Observe what are the 10 things that you see in this picture. First, write. First, circle them in the picture.
Electron cloud. Okay? ఓకే ఫైన్. అంటే క్లౌడ్ అంటే ఏంటంటే కొంత డిస్టెన్స్ వరకు మనకి ఎలక్ట్రాన్ యొక్క ఎఫెక్ట్ అనేది ఉంటుంది. ఓకే, జనరల్లీ ఇన్ కెమిస్ట్రీ విల్ స్టడీ అబౌట్ ఎలక్ట్రానిక్ ఎఫెక్ట్స్. ఓకే, అయితే ఇప్పుడు ఈ మధ్యలో ఏంటంటే మన క్లౌడ్ అనే పదం బాగా వింటున్నాం. మీరు ఒక సిస్టంలో కానీ లేకపోతే బయట డేటాలో కానీ ఏదైనా వాట్ టైప్ ఆఫ్ డేటా ఇట్ ఈస్, ఎనీ టైప్. ఓకే, క్లౌడ్ డేటా అంటారు. ఓకే, ఎనీథింగ్. ఓకే, క్లౌడ్ అంటే ఏంటంటే కాంబినేషన్ ఆర్ కలెక్షన్ ఆఫ్ డేటా ఆర్ ఇన్ఫర్మేషన్. ఓకే, ఇక్కడ ఏంటి ఎలక్ట్రాన్ క్లౌడ్ అంటే కనుక దీని ఏమంటాం, ఒక ఎలక్ట్రాన్లో మెనీ సబ్ పార్టికల్స్ ఉంటాయి. మెనీ సబ్ పార్టికల్స్ ఉంటాయి. ఆ సబ్ పార్టికల్స్ అన్నీ కలిపితే మనకు ఒక క్లౌడ్గా వస్తుంది. దాన్ని మనం ఏమంటున్నాం అంటే ఎలక్ట్రాన్ క్లౌడ్ అంటున్నాం. ఎలక్ట్రాన్ క్లౌడ్ అంటారు. అయితే ఇప్పుడు ఛార్జ్ కన్సర్వ్ అవ్వాలంటే ఈ ఎలక్ట్రాన్ క్లౌడ్ చుట్టూ నాకేముండాలి, ఒక పాజిటివ్ క్లౌడ్ ఉండాలా? అవునా? హలో, ఈ పాజిటివ్ క్లౌడ్ని మనం ఏమంటామంటే హోల్ అని అంటున్నాం. ఈ పాజిటివ్ క్లౌడ్ని మనం ఏమంటున్నాం అంటే హోల్ అంటున్నాం. అంటే ఎప్పుడైనా సెమీ కండక్టర్లో ఒక ఎలక్ట్రాన్ని ఎగ్జైట్ చేసామనుకోండి హైయెస్ట్ ఎనర్జీ స్టేట్కి, ఫస్ట్ ఎగ్జైటెడ్ స్టేట్ కానీ సెకండ్ ఎగ్జైటెడ్ స్టేట్ కానీ, అప్పుడు ఏముంటుంది అంటే మనకి పాజిటివ్ క్లౌడ్సే ఉంటాయి. అవునా? ఇప్పుడు ఫర్ ఎగ్జాంపుల్ నాకు ఏదైనా ఒక కాన్ఫిగరేషన్ తీసుకుందాం, 1s2 2s2 2p6 3s2 3p1 అంటే అల్యూమినియం తీసుకున్నాం అనుకోండి. నాకు వ్యాలెన్స్ ఎలక్ట్రాన్స్ 3 ఉన్నాయి. ఈ 3 ఎలక్ట్రాన్స్ ఎగ్జైట్ చేశాను అనుకోండి, 3 ఎలక్ట్రాన్స్ని నేను ఎగ్జైట్ చేశాను అనుకోండి, అప్పుడు నాకు 3 హోల్స్ ఉంటాయా? హలో, 3 హోల్స్ వస్తాయా? అయితే నేను ఎలక్ట్రాన్స్ని ఎగ్జైట్ చేయటం వల్ల లేకపోతే ఎనర్జీ సప్లై చేయటం వల్ల ఏమైంది, ఎలక్ట్రాన్స్ ఆర్ గోయింగ్ టు ద ఫస్ట్ ఎగ్జైటెడ్ స్టేట్ అండ్ సెకండ్ ఎగ్జైటెడ్ స్టేట్. డ్యూ టు దట్ ఓన్లీ holes are formed. That is, the generation of the hole, okay, will happens whenever electron is excited to highest energy states. Okay, what will happens to the whenever the electron stays in ground state? In the ground state, will the holes will be exist or not? గ్రౌండ్ స్టేట్లో నాకు ఎలక్ట్రాన్స్ అనేవి హోల్స్ అనేవి ఉంటాయి ఉండవా? కదా, ఎందుకంటే ఇన్ ద గ్రౌండ్ స్టేట్ వీఆర్ హ్యావింగ్ ద ఎలక్ట్రాన్స్ విచ్ ఆర్ ఎట్ రెస్ట్ ఆర్ విచ్ ఆర్ సర్క్యులేటింగ్ ఇన్ ఇట్స్ ఓన్ ఆర్బిట్. Okay, so in a semiconductor, okay, the majority or major constituents are, in a semiconductor the major constituents are holes and electrons. Okay, suppose number of electrons, I will write it as Ne. Number of holes, I will write it as H. Okay, Ne, it is the number of electrons. Number of electrons. NH, it is the number of holes. Now, in any semiconductor, generally what will happen, in order to have the charge conservation, number of electrons must be equal to number of holes. Avuna? Okay, number of electrons must be equal to number of holes. So, conductivity of the electrons must be equal to the conductivity of the holes. Is it right? Okay, so this happens pretty well or very good in the pure semiconductor. Pure semiconductor. Pure semiconductor means I can say intrinsic semiconductor. Intrinsic semiconductor. Can I say? Okay, that is which is available from the earth crust. So for intrinsic semiconductor, I can write it as intrinsic semiconductor. I can write as conductivity of intrinsic semiconductor. That is conductivity of the electrons times the conductivity of the holes. Since it is intrinsic semiconductor, I am writing it as sigma I. Sigma I. That is, here we are having the conductivity of intrinsic semiconductor is equal to sigma E times sigma H. Sigma E times sigma H. Here they gave that it as, okay, we are having a law which is called law of mass action. According to this, they gave that square of the number of particles in the intrinsic semiconductor, square of the number of particles in the intrinsic semiconductor is equal to number of particles in the number of electrons in the given semiconductor times the number of holes in the given semiconductor. Number of holes in the given semiconductor. That is Ni square is equal to Ne into Nh. Ni square is equal to Ne into Nh. Where Ne is the number of electrons per unit volume. And this one also, Nh is the number of holes per unit volume. Now, tell me one thing, number of particles per unit volume can be called as, మీరు కెమిస్ట్రీలో ఎప్పుడైనా నెంబర్ ఆఫ్ పార్టికల్స్ పర్ యూనిట్ వాల్యూమ్ అని వచ్చిందా? హలో, నెంబర్ ఆఫ్ పార్టికల్స్ పర్ యూనిట్ వాల్యూమ్ ఫిజికల్ కెమిస్ట్రీలో మీకు వచ్చి ఉంటుంది. ఏమని? కాన్సన్ట్రేషన్ అని. చదువుకున్నారా? హలో, concentration we can write it as number of particles per unit volume. Is it right?
Yes, sir.
Okay, అయితే okay, number of particles per unit volume. Now here we are having that it is, we are having the intrinsic semiconductor whose number of particles per unit volume it is Ne and Nh. Correspondingly we are having conductivity. The relation between conductivity and mobility, that is I can write as Ne mu. కరెంట్ ఎలక్ట్రిసిటీలో మీకు రిలేషన్ వచ్చిందా? ఇది సిగ్మా ఈక్వల్ టు ఎన్ఈ మ్యూ. హలో, చరణ్, గాయత్రి, శ్వేత, మీకు ఈ రిలేషన్ వచ్చిందా రాలేదా? రాకపోతే నేను డిరైవ్ చేస్తాను. రిలేషన్ వచ్చిందా రాలేదా నాన్న? We know that current density is equal to J equal to sigma E. అవునా? Yesterday we derived it. Okay. Mobility, it is defined as number of electrons, okay, which are moving inside the conductor, okay, with an unit amount of electric field applied. Suppose we are having a conductor. Whenever I connect to a battery, okay, battery is having a potential V. Correspondingly, we are having an electric field E. With this electric field, okay, this electric field pushes the electrons and protons inside the conductor to move with a velocity which is will call as an drift velocity. Drift means the particles are moving whenever an energy is applied. That type of motion can be called as drift motion. So here mobility is defined as ratio of drift velocity of the electrons to the per unit amount of electric field applied. Okay, fine. So Vd is equal to mu E. Ram, మోస్ట్లీ ఈ సంవత్సరం మొత్తం క్లాసులు అన్నీ ఇట్లాగే ఉంటాయి. మీరు ఆటలాడుకుంటున్నావు, పాటలు పాడుకుంటున్నావు, నేను క్లాసులు వింటాను అంటే మళ్ళీ మీకు మార్చిలోనే ఎగ్జామ్స్ ఉంటాయి. ఆల్రెడీ 10th క్లాస్ వాడికి, ఇంటర్మీడియట్ వాళ్ళకి బోర్డు డేట్స్ అని డిక్లేర్ చేసేసింది. అందుకని దయచేసి మీరు ఇంట్లో ఉంటున్నా కూడా, కాలేజీలో ఉంటున్నాను నేను చదువుకోవాలి అన్న దూరంలోనే ఉండండి. అట్లీస్ట్ ఫ్రమ్ 9 AM to 6 PM. 9 AM to 6 PM ఈ టైంలో మీరు చదువుకోవాలి, ఇదిలోనే ఉండండి. డోంట్ గెట్ డీవియేట్ టు ఎనీవన్. ఎందుకంటే గవర్నమెంట్ ఒక్కసారిగా మళ్ళీ అనౌన్స్ చేసేస్తుంది, మళ్ళీ ఎప్పుడో బండి వేస్తుంది, మార్చిలో ఎగ్జామ్స్ అంటుంది. అప్పుడు నష్టపోయేది, ప్రెషర్గా ఫీల్ అయ్యేది మీరే. మాదేమన్నా సిలబస్ అయిపోయిందంట, చదవాల్సింది మీరే. అందుకని రోజు కొంచెం కొంచెం చదువుకుంటుంటే ఆ భారం తగ్గిపోతుంది. Drift velocity I can write as mu E. So mobility explains about the motion of one electron. Or motion of one electron means I can say conduction for one electron. Conduction for total electrons. Suppose if we are having n number of electrons, let us consider small n is the number of electrons in the conductor. Small n is the number of electrons in the conductor. Then the total charge I can write as Ne. Okay. So here we are having the conductivity. For one electron, motion it is mu, mobility. For n number of electrons, the conductivity I can write as Ne mu, Raja. With respect to this drift velocity, we'll have the drift current ID అంటే NEAVD అని వచ్చిందా ఈక్వేషన్. దిస్ NE I can write as okay the total number of electrons, or I can say it as number of electrons per unit volume, that is electronic concentration. Electronic concentration, okay, like this. Okay. So here we are having conductivity equal sigma equal to Ne. Now I am having an intrinsic semiconductor. Now what I want it is, as the temperature increases, what happens to conductivity of intrinsic semiconductor? What happens to conductivity of intrinsic semiconductor? This one I want to find. Okay, we'll continue tomorrow. Okay, let's stop here for today. Okay, na?